supervised learning that has made a huge impact across the world. And now we are increasingly turning our attention to more general problems in general artificial intelligence that will enable agents to learn on their own and to act autonomously in the environment. So some examples include training an agent to play a complicated board game, or training an agent to drive a car, or training personalized assistants that can help around the house. So in this talk, I'll give a brief overview of some of the big challenges in achieving these goals and even more ambitious goals, and some techniques that have been developed to address them. So what are some algorithmic challenges in reinforcement learning? First, it should work well on data encountered in the real world. And this includes data with temporal dependencies and when there's distribution shift between the training data set and the real world data. And also in general, algorithms should be data and computationally efficient. And so the problem of reinforcement learning is the setting where we have an agent that is interacting with the environment by taking actions and earning rewards and then transitioning to the next state. So the observations are the state, action, reward, next state tuples that the agent gets from the environment. My cursor is not working. Okay, so the environment is normally modeled as a Markov decision process where we have states S, actions A, rewards are bounded between 0 and 1, and P of S prime given SA is the transition probability to state S prime by taking action A from state S. And we have a discount factor gamma between 0 and 1 that discounts the present value of future rewards. And in reinforcement learning, we're often concerned with policies pi that are mappings from the states to actions that tells an agent what action to take at any given state. And we evaluate better or worse policies using their value. So V pi is the expected infinite horizon sum of discounted rewards from starting at state S naught, taking action A, and transitioning according to the dynamics of the environment. And so the first problem is that typically in reinforcement learning data or data sets from the real world, there is a temporal dependence in this data set. And temporally dependent data slows down learning because subsequent observations that you see are very close to each other. And so one way that people have developed and practiced to deal with this is to use an experience replay to break temporal dependencies and to speed up learning. So to experience replay works in the following way. We save transitions, state, action, reward, next state into a buffer, and then we sample from this buffer. And we use the samples from this buffer to train the agent so that subsequent observations that the agent sees are not going to be as temporally dependent. They're going to be closer to an IID case. And so we study experience replay in the context of least squares regression. So we have our observations y equals to x transpose w star. W star is the learnable parameter, and x is Markovian data. So our features x come from a Markov chain, which is the autoregressive chain, which is sort of like a random walk. And we want to minimize the out of population loss of a sample from the stationary distribution. So that's our loss. And so our main result is that SGD with experience replay for the autoregressive chain can speed up the learning. So we show an upper bound for SGD with experience replay that where the loss decays exponentially in the number of time steps over the square root of the mixing time. And we show a lower bound for sequential SGD, so without experience replay, where the loss decays exponentially in the number of iterations over the mixing time. So if we plot the log loss on the right, we see that the loss for SGD with experience replay is bounded in the green region, and the loss for sequential SGD is in the red region as a function of the number of iterations t. And this is one of the first analyses for experience replay. Oh, okay. And the second, main challenge in reinforcement learning is the issue of distribution shift between the training data and the real world data. And this is particularly relevant in the case of offline reinforcement learning. So in many real world scenarios, the deployment of a poorly understood policy for the purposes of online learning can be too costly or too risky. So we must rely only on the offline data set to find a reasonable policy for deployment. And so say that we have a fixed data set of trajectories collected by some behavioral policy, S naught AR, that is not coming from the policy that you're actually interested in understanding. So there is a distribution shift between the two data sets. And we also want to look at the problem of off-policy evaluation, which arises in two main contexts. So the first is a ranking problem. Given a set of potential target policies that you're interested in for deployment, pi 1 through pi n, evaluate them and pick the best one to deploy. Could be the highest value policy or the safest policy. And the second situation is for offline learning. So as a subroutine for offline learning, agents need to iterate towards better policies based on accurate value estimates from off-policy evaluation. And so we mainly focused on the problem of ranking. And one very popular algorithm for off-policy evaluation is fitted Q evaluation. And in terms of accuracy, recent papers have shown that it achieves state-of-the-art accuracy. However, there is also work out there that talks about the stability of FQE. In particular, it can diverge to plus or negative infinity for both linear and nonlinear function approximation. So we wanted to understand how architecture and representation affects stability and accuracy for FQE and variance. So we started off with a very popular model in deep learning, which is the multi-layer perceptron with layer normalization for the input layer. And then for FQE, using this architecture for for many of the DeepMind control suite tasks, we see a lot of instability, wild oscillations, and in the last two figures, divergence to plus or minus infinity for the value estimates. And we saw that architectures that use implicit regularization can improve stability without sacrificing the accuracy of the overall estimate. And so we have a few examples of better architectures on the bottom. For example, using a ResNet or using a distributional FQE, which is a different loss. It's a distributional loss, not an L2 loss. So this is more in line with the work on distributional RL. And the third one is a architecture that is inspired from multitask learning. So FQE with a shared representation. And the last one is FQE with a hypermodel, which is basically trying to smooth out an ensemble. It's an ensemble at scale. And so there's implicit regularization there. And in the last part of this talk, I'll talk about general data efficient algorithms in the presence of a generative model. So in the presence of a generative model, a simulator produces samples of S prime for any state action pair with probability P of S prime given SA. And so the algorithm gets to query from the simulator to learn the optimal policy. And this is useful for certain applications where simulators exist or are easily constructed. For example, video coding applications or physics simulators for robotics, such as the control suite tasks. And our result is a model-free minimax optimal method for finding the epsilon optimal policy. And there are also model-based minimax optimal methods using a generative model as well. And so our main result is that we can compute an epsilon optimal policy with high probability using sample complexity and runtime that is logarithmic in 1 over epsilon. And this is nearly linear. This is a nearly linear time, nearly linearly convergent algorithms for solving discounted MDPs. And we have a second algorithm that computes an epsilon optimal policy with high probability and sample complexity and runtime that is cubic in 1 over 1 minus gamma. And this is nearly optimal up to log factors and sample and runtime complexity using only the generative model. And so in conclusion, my research or my goals are to build solutions that are simple, easy to understand, explain, and engineer, effective, that they work well in practice, and also are theoretically well-grounded. Thank you.
Thanks, Carrie. Got some questions? Could you maybe tell us a little bit about where the logarithmic dependence on epsilon arrives in the positive result about with the generative model?
Yeah, it's a variance reduced value iteration method. So I don't know how well the audience is familiar with value iteration, but it's a successive approximation method. Basically, you like solve for, it's an iterative method, right? You start off with a value vector, and then you use the Bellman updates, and then you're getting closer and closer to the true value function via a fixed point contraction mapping properties of the Bellman operator. And so basically when you use that with a generative model, basically when you have a generative model, you use the simulator to produce samples of S prime. So basically the algorithm will query from the simulator to get samples of S prime from the like according to the real transition probabilities. And so instead of having like exact value iteration exact value iterations, you have like approximate value iterations. And then so our variance reduced method on top of that, it's very simple and it's inspired by like variance reduced SGD that's already out there. Basically, we save milestone vectors along the way so that instead of querying from the previous value vector, we're gonna query from like these milestone query vectors or value vectors. Sorry, if that makes sense.
Thanks very much.
Yeah.
All right, thanks again, Jen.
Mhm.
And the last speaker for this session is